Hey guys, so this is the video that is just going to basically finish off the Chapter 5 material. What we're dealing here in this video is with kinetic molecular theory and really the difference between ideal gases and what we call non-ideal or sometimes called real gases. So let's get into it. So essentially, let's start by just writing kinetic molecular theory on the board. And what I would say is just take notes off this as if we were in class, just the same way. All right, so first of all, a little bit of talk about the concept of theories. Remember, in the gas chapter, we've been learning a lot of laws. Boyle's law, Charles' law, ideal gas law, so on and so on. Dalton's law of partial pressures. Remember, a law is a series of related observations, something that a scientist sees over and over and again, in many different contexts, many different labs. The difference between a law and a theory is really relates to the unseen. It's really the backstory, and what it does is it describes why matter behaves as it does. So because theories deal in the realm of the unseen, in other words, what we're doing with theories is modeling matter to explain the laws that we actually can observe and that are proven because we can observe it. Theories, there's an element of unfinishedness to a theory. In other words, we can revise a theory based on new data or new discoveries. And so a theory is really just our best guess at explaining why we see what we see. So that's what we're doing with kinetic molecular theory. Kinetic molecular theory is attempting to explain Boyle's law, Charles' law, Avogadro's law, etc. When we are doing or describing kinetic molecular theory, the model or the mental picture that we are using is the one that we've been using all along. So to some extent, we've already been using kinetic molecular theory, which is that if you have a gas container, let's put a lid on it so nobody can escape. If you have a gas container, the gases themselves are molecules or atoms, just depending on what kind of sample you have, and that they're very spread apart from each other. In fact, most of the gas sample is actually empty space. And the gases are in constant motion. So what we're going to do is draw straight arrows. And that really is going to indicate two things. Number one is that the gases are in constant motion, which is what I just said. But also they move in straight lines. And that's the mental picture that we are picturing when we are exploring kinetic molecular theory. Now, sometimes they hit each other, they collide with each other, but sometimes they hit the sides of the container, which of course creates pressure. That's where your pressure comes from, where they're colliding with the side of the container. So this whole theory is using this mental picture as our model. Now, kinetic molecular theory has what we call three postulates, three proposals, three statements, that we are declaring about gases that will account for what we see with these laws. So let's go ahead and put these three postulates down on paper here. So number one, postulate number one, the size of the gas particles, whether they be atoms or molecules, the size of the gas particles is negligible compared to the space between them. And so in science, math, negligible means not zero, because gas particles are matter and they do occupy space. So we're not talking about zero, but negligible means so small compared to the space between them that we can almost ignore it. We can consider it to be zero. It's insignificant. So that's actually the first part of this, is that the space between the particles is so much larger than the particles themselves that we can ignore the actual size of the particles themselves. Obviously, they do take up a little bit of space, but we can ignore it. That's postulate number one. Postulate number two, Oh, actually, you know what? Before I move on from postulate number 1, this explains why gases are compressible. And that's because there is so much empty space between the particles that there is room to push them together. Whereas, if you consider solids or frankly even liquids, they're going to resist compression because there's no space to put the particles. They're already basically as close to each other as possible. So that's why gases are compressible. And actually, frankly, this is also why, so that's point number 1. This is also why gases act independently. That's actually a big part of this too. So let me make sure I write that down. Remember when we were talking about partial pressures, the gases don't really tag team. They don't team up. They really all just do their own thing, exerting their own pressure on the sides of the container because they're not close enough to interact. We haven't talked much about intermolecular forces, but they're not going to interact with each other because they're so far from each other. And when they hit each other, which we'll talk about in a subsequent postulate, they're just gonna move straight off of each other. All right, so postulate number 2 is, let's see here, how are we going to say this? Okay, the kinetic energy, or let me write this, the average kinetic energy of the gas particles is proportional to the temperature in Kelvin. Okay, so we know that all of these gas laws work when we're using Kelvin as our temperature unit. So let's take a minute and talk about kinetic energy because this is something that I do want you to know. Kinetic energy has an equation. Obviously, kinetic energy is the energy associated with motion or movement. The equation for kinetic energy is 1/2 mv squared. That's an equation that I do want you to have memorized. Little m, remember when it's a unit, it stands for meters, but when it's a variable in an equation, it stands for mass. And little v stands for velocity. And that's why we have to be careful that we're not using capitals when lowercase is required. Little v is velocity. All right, so that's the equation for kinetic energy. So the first thing I want to say is that the higher the temperature, the greater the kinetic energy of the particles, and most people come knowing that. When you raise the temperature of anything, whether it's a solid, liquid, or a gas, the particles are going to have more energy, they're going to move more. So that part is not too much of a surprise. And actually, if you would have your book open, because I actually wanted to show you, and I'm not going to draw it, but I do want to point out to 2 graphs in chapter 5 on page 227. So let me give you a second to grab your book. But page 227, the first graph I want to show you is figure 5.19, which is the one on the right. It is a fairly straightforward graph, but what you're looking at here is 3 different samples of a gas. Actually, it's always the same gas, so it's on the figure on the right, it's always nitrogen molecules. And what you're looking at with the 3 different curves is an increase in temperature. And what you're seeing here is that as you increase the temperature, the particles are actually moving faster. Notice on the x-axis, it's molecular velocity. So because as you increase the temperature, the kinetic energy is increased, because the mass obviously is staying the same because it's all nitrogen, the velocity is increased. So I know that's not rocket science, but as you raise the temperature, the molecules are moving faster. So that's the first thing that I wanted to say about that. One thing real quick though is that the molecules are not robotic. There's not a single velocity that they move at. If you notice, it's a bell curve. There is an average velocity for any gas sample. Some of the gas samples, for instance, if we look at 2000 Kelvin, some of them are moving a little bit slower. Some of them are moving faster, but there's an average, just like a grades in a class. There's an average. So that is the one thing I wanted to mention about that word right there, that there is a distribution of velocities. The second part of this relates to the other figure on page 227, the one on the left. What you're looking at here is various different types of gases, so H2, so hydrogen, helium, water vapor, nitrogen, and oxygen. And what you'll see is that the one that's moving the fastest is the hydrogen. The one that's moving the slowest is the oxygen. So let's talk about that for a minute and explain this graph, because this is another concept that I do want you to have an understanding of. At any one temperature, so in figure, let's set what figure this, that is figure 5.18. What is the temperature that these things are being read at? These samples are all at 25 degrees C, which is 298 Kelvin. Okay, so they're all at the same temperature. However, so they all have the same kinetic energy. So that's what I wanted to say. If they're at the same temperature, they all have the same temperature, means they have the same average kinetic energy. However, if they all have to have the same average kinetic energy, which they will average, then the ones that are actually smaller in mass will have to have a greater velocity in order to make up for the to meet this requirement of having the same. And if that doesn't totally make sense to you, just think about a mathematical thing here. We have, I'll just put the number 100. Okay, let's just think of two numbers that get multiplied to make 100. So let's go 5 and 20. Okay, and then 10 and 10. So what I'm trying to say is that the ones with the smaller mass, in this case the number 5, will have to have a greater velocity, in this case the number 20. So if we wanted to make a clean-cut statement, it's this. Smaller particles, and when I say smaller, I'm talking about in mass, move faster. And larger particles move slower, okay? That makes perfect sense. Picture a race car versus a semi-truck. Semi-trucks, just because they're so much more massive, do not move as fast with using the same amount of gas versus a race car, which is smaller. So that's just a physics concept, frankly. But I did want to point that out. That's what that second graph in figure 5.18 is trying to show you. The reason hydrogen is moving so fast is because it's so small. Okay, so that's what I wanted to mention about this second postulate. Let's move on to the third postulate. I'll have to erase a little bit of space here. So the third postulate of kinetic molecular theory states that the collision, so these are like assumptions, okay, so things that we're just assuming is true. The collisions between particles are completely elastic. Okay, so elastic. So we know about an elastic rubber band or whatever. So we have some concept of what that word means. But to get the best picture of this, I'm going to refer you also to your book. Let's take a peek at page 223, figure 5.16. You have a nice little picture of an elastic collision versus an inelastic collision. An elastic collision is like the billiard balls in the picture. Okay, so let's go ahead and give you a definition for elastic, and then you can picture the billiard balls. Elastic means that the particles can exchange energy. They can exchange energy. In other words, like for instance in pool, the white ball, when you hit it, can give its energy to another ball. Okay, so you can have an exchange of energy. However, but there is no overall loss of energy during a collision. Back to the pool. In pool, obviously, it's not a perfect metaphor, because in pool you would have some friction between them and you would lose a little bit of energy. But it's the best example that we can give in real life. So in the picture, elastic collision, you can see the energy that they came in with, they also leave with. Okay, so that is an elastic collision. And if you think about that, that makes perfect sense. Otherwise, every time they collide, you would actually lose energy and samples would just get colder with time because they would just lose energy. And that's not really what's happening. An inelastic collision is modeled here as two pieces of clay coming together, whereas when they interact with each other, they are going to kind of stick to each other and you'll lose energy. They're not going to actually leave with the same amount of energy that they came in with. So that would be an inelastic collision. But we are assuming, based on kinetic molecular theory, that all of our collisions are perfectly elastic. All right, so that is the three postulates of kinetic molecular theory. Now, what does all of this, how does all of this come together? Really, it comes together kind of from this point here, PV equals nRT. This thing here is called the ideal gas law. And like I mentioned before in class, the word ideal is more about is an adjective for the word gas. It's not the best law. That's not what it means. But it's the law that applies to ideal gases. So what are ideal gases? Ideal gases are gases that conform to all three postulates of kinetic molecular theory. In other words, they obey these statements that I just put on the board. They do have particles that are so small in size that we can ignore the size. They do have average kinetic energies that are proportional to the temperature, and they also do have elastic collisions, perfectly elastic collisions. So because they obey all three postulates, then they will obey this equation perfectly, which means that if I was to be able to measure, say, volume and pressure and temperature, for instance, then I could actually just calculate and be quite confident that my number of moles is exactly what I think it is, because these are ideal gases. So it's really all about are their properties perfectly predictable by the ideal gas law? And as long as they conform to those three postulates, then we can be sure that they are. And that's very nice. So now that we've gone through these postulates, we can actually now discuss what are called real gases, or non-ideal gases. What are the times when this law will not work for us per se? So let me go ahead and erase this. All right. So let's talk about non-ideal, sometimes known as real gases. And by the way, you know, I'm making kind of this huge divide, but of course, in science, it's more of a continuum. So it's a little bit more about how exactly perfect you want to be with your data. For us in the class, we are always assuming everything is ideal. If I give you properties of a gas, you just assume you use those laws that I gave you, and that's perfect. But I do want you to have this concept down, and I also will ask you a little bit about the two conditions that I'm going to put on the board. So you are required to know, you know, the concept of what is a real gas. All right, so non-ideal real gases. Let's say it like this. There's two conditions, and I want you to know the two conditions. So at very high pressures, like I said, I'm not giving you a boundary because it's a continuum, but let's just think very high, and that's good enough, or very low temperatures. The kinetic molecular theory postulates, let's just say, break down in one way or another, and we'll talk about which ways in just a second. And the gas behaves non-ideally, which means it's not going to perfectly obey this equation, PV equals nRT, okay? So there's going to be some deviation from the properties that you would expect. Let me just mention right now that there is a man named Johannes van der Waals. I want you to know his name. Van der Waals studied non-ideal or real gases and modified PV equals nRT so that it would work for real gases. Essentially, there's some addition to the equation that he discovered or figured out. And we are actually not going to be using the van der Waals equation in this course, but I do want you to know that the van der Waals equation is a modification of PV equals nRT, and that's what it's for. So I want you to know that it deals with real gases, and it was him who figured it out. So that's the level that we're gonna need to know about van der Waals, mostly his name and what did he do. All right, so I'll mention that. Now, let's talk about these two conditions. How do they violate kinetic molecular theory, and what happens? All right, so let's talk very high pressures first. And once again, when you're talking about gas samples, especially if you're dealing with issues with pressure and volume, it's quite nice to draw a little piston that you can actually move. It diagrams this very simply. So let's talk about these two conditions. So this is what we would consider, let's just do, 5 particles here. This would be considered, let's just say average pressures, okay? So I know it's not, quantitative, but let's just call this the average pressure, and this would be considered the ideal. And you know what, let's just say low or average pressure would be an ideal gas. Everything is fine, PV equals nRT, all is well. But what happens when we actually compress this gas to such a state that the pressure is very high? According to Boyle's law, because we have lowered the volume, we have absolutely increased the pressure. And let's go ahead and say that we've increased it very high pressures. And this is just, I know the drawing is not perfect, but this is just to diagram very high pressure. What postulate of kinetic molecular theory does this violate? Think about that for a second. Postulate number 1, postulate number 2, or postulate number 3? Maybe you were able to think about it. It has absolutely nothing to do with postulate number 2 or 3, but it does violate postulate number 1. So postulate number 1 is violated. Why is it violated? Well, postulate number 1 said that the size of the particles is negligible compared to the space between them. But when you have very, very high pressures, you literally minimize the space between them so that now the actual size of the particles becomes important. You can't ignore it and pretend that it's 0 because it's actually quite a big part of it. So that's why at very high pressures, that whole postulate breaks down. And once one postulate breaks down, then kinetic molecular theory is not really being satisfied, and these gases are going to be considered non-ideal or real gases. What happens in this situation is this type of Boyle's graph. Let's go ahead and draw a Boyle's graph here. Remember, volume is always on the x-axis for these. Pressure would be on the y-axis. Sorry, I got those backwards, but you know what I mean. The general shape of Boyle's graph data looks like this. Okay, so let's go ahead and I'm just putting some data points here. Let's call this the ideal gas. And I'm not sure. Let me see if I have another color. Yeah, maybe this blue will work. So that's an ideal gas. At low pressures, any gas sample is going to act totally normally. So it's just completely the same as an ideal gas. So we're not going to have any deviation at low pressures. But as the pressure gets high, what's going to happen is the volume is actually going to be larger than what you would predict for an ideal gas. So let's go ahead and write this as a non-ideal or real gas. And what you're looking at here is called a positive deviation. Positive deviation is a larger number than what you would expect or what you would calculate. And the reason the volume is slightly larger is because rather than counting the particles rather than discounting the particle's volume, it now becomes important, and it becomes not negligible anymore. So it will actually give you a volume based on that includes the volume of the gas samples, and you're going to have a greater volume than what you would have predicted. So what I want you to know is the condition, but I also want you to know why. And the reason is because the volume of the gas samples becomes important because the space between them has shrunk, and that you're going to get a positive deviation in volume. And that's good enough for that concept. Now, the last concept is what's the deal with very low temperatures? So let me go ahead and erase this. So at very low temperatures, why is that an issue? So this one's a little bit more hard to diagram just because it's hard to draw temperatures on a board. But let's go ahead and draw something like high temp. Well, let's see here. Let's say at high or average temps, and then let's go very low temps. All right, so at higher average temps, we've got, let's just draw 3 for this example. We have obviously particles in constant motion. And at high temperatures, they're moving so fast that they just come at each other and have a perfectly elastic collision. So what we would say at high temperatures, or at least average temperatures, the collisions are elastic. Because they're just coming at each other so fast. Picture two I don't want to keep using, just picture 2 balls coming at each other really fast. They're just going to bounce right off of each other. Whereas when you have low temperatures, and this way, let's see if I can diagram this maybe with a dotted line, where these particles are approaching each other so very slowly because they're moving so slowly because of the low temperatures. As they are approaching each other, there's actually time for interaction. And that interaction is going to be a slight attraction because of intermolecular forces. The type of intermolecular forces we will save for a later chapter, but for right now, just think of them as they're approaching each other. They're going to be slightly attracted to each other, and they'll start to exchange a little bit of energy, and you'll actually lose some energy to the interaction. And what happens here is we would call this an inelastic collision. Inelastic collision. So when you have very low temperatures, you violate which postulate? You violate postulate number 3. And it's because of the interaction between particles as they approach each other so very slowly. And what is going to happen here is obviously this will create a real or non-ideal or real gas. Whoops. And of course, this one here was an ideal gas. The deviation that we would see will look like this. For this one here, what we're going to do is just contrast pressure to temperature. So a little bit of a different type of graph than we've drawn before. So let's have 2 separate lines here. So first, let's do the ideal gas. So what we're seeing here is that as temperature is decreasing, pressure is decreasing. Actually, this is related to a law that we didn't talk too much about called Gay-Lussac's law. But as temperature is decreasing, pressure is decreasing. And the reason is because as they are moving slower, they are going to collide less often and with less force with the wall. So we've talked enough about this that should make some sense. So as they are moving slower, they collide less often and with less force with the walls of the container, which decreases your pressure. However, at very low temperatures, that effect will even be more increased because not only are they moving slower, but now they're interacting with each other a little bit when they collide. And so what you are going to see with a real gas is that at high temperatures, no big deal, everything's the same. But as those temperatures get lower, you're going to see what's called a negative deviation in pressure, meaning the pressure will be even lower in this sample than you would have predicted with PV equals nRT. It's not going to be, PV equals nRT will not give you a perfect pressure. That's what van der Waals did to fix. He modified the equation to make it work. But it'll be lower than even expected because of that interaction. So that is the two conditions that violate kinetic molecular theory that kind of move us from talking about ideal gases to real gases. Now, look in that study guide, that chapter 5 study guide. I have a little note there that there are some vocabulary words in this chapter that you are required to know. I want to say they are kind of in section 5.9. I can't quite remember what I put on there, but if I told you to learn vocabulary words on the study guide, make sure you at least know the definitions, that you might see a question or two on the multiple choice dealing with that. So hopefully that was good. I don't even know how long that took, but hopefully you took notes, and this material will be on the upcoming exam. So I hope you're enjoying your spring break. Good luck studying, and I'll see you when you get back. Bye-bye.